Okay, so we've now had a good look at the bivariate PDF. So we've got two continuous random variables. They have a bivariate structure. So we're going to look at a classic named bivariate, and we're going to look at the bivariate normal. So let's do a setup. We've got two random variables, x and y, and we've got such that we know the expected value of x is mu of x, and the expected value of y is mu of y. So we've just got some expectations. We've also got that we're going to denote the variance of x as sigma x squared and the variance of y as sigma y squared. But we've also got some sort of relationship between them, so we know that the covariance of x and y is rho, which obviously is going to be the correlation coefficient, sigma x, sigma y. So we've got all that detail. Well, we can describe this as what we call the bivariate normal distribution. So it's complicated, but let's break it down. So we've got the joint PDF of x and y. First of all, it's this. We've got a complicated term in the expected. But if you look at it, first of all, this whole term, expectation, x, the e term, is very similar to what we expect from a normal. And this bit here, we've got our 2 pi, and we've got some sort of variance term, which is very similar to the univariate normal. And then our q, we've got sort of x minus mu x, which is what we'd normally expect. We've also got a y minus mu y, and then we've got our cross product term. And if we have two random variables, x and y, that have all the expected values and variances, covariance we see, and they have this joint probability mass function, probability density function, we say they have a bivariate normal distribution. So this is quite messy, so let's think about how we can sort of do better notation. Well, first of all, we often write our x and y as what we call a random vector. So now we've got this little column vector where the first entry is a random variable x and the second entry is random variable y. We say that is simulated normal. The first term is our expected values, and then we've got this sigma to represent the variance terms. What does mu mean? Well, mu is going to be, in this case, a 2 by 1 column vector, where the first entry is the mean of x and the second entry is the mean of y. And this sigma is called our variance covariance matrix. It's going to be a symmetric matrix. It's actually going to be what we call strictly positive definite. But generally, it contains all the variance covariance information. So you find on the diagonal, we will have the variance terms. And off the off diagonals, we have the covariance terms between them. So what if we wanted to get the marginals? What if we had that bivariate probability density function and we wanted to get the marginal distribution of x? Well, the nice thing is it drops out very easily, and the marginal distribution of x is just a normal distribution with a mean of mu x and a variance of sigma x squared. And the same for the marginal distribution of y. It will be normally distributed with a mean of mu y and a variance of sigma y squared. The conditional is an interesting one. It comes in very useful. In third year, you get to do a computational Bayesian course. You'll use this a lot. So basically saying, what is the distribution of y given we know that x equals x? So not the marginal, but the conditional distribution. Well, what you do is you take the mean of y and you add this adjustment factor. And what's our adjustment factor? It's going to be how far x is away from its mean. And then you've got this rho sigma y over rho, sigma x. If you've done linear regression, not all of you will have done, but if you do linear regression, you'll notice this looks very similar to your estimate of the slope. Well, it's a population version. And the sigma will be your sigma y squared adjusted by the amount of correlation you've got between these two variables. We could also, I'm just going to quickly show you, I don't expect you to know this, but the multivariate version, how could we take it if we had 3, 4, 5, etc. So now we're going to have k random variables, x1 up to xk. We're going to have that the expected value of each x has its own expected value, its own variance, and we're going to denote the covariance as sigma ij. So this is our new normal. We've got our 2 pi term. Basically, we've got k of them, so we take the kth power and we take the square root. We've got here, what this is saying, that we take our variance covariance and we get the determinant, so those two lines either side indicate determinant, and we take the square root of the determinant, which is like your sigma term in your normal univariate. We've got exponential, and now we've got basically x minus mu squared. So this is the matrix version of x minus mu, so this is x minus its mean squared. And then normally we would have 1 over 2 sigma squared, where instead we've got 1 over 2, and obviously we can't divide by matrices, instead we have sigma to the minus 1. And our x in this case would be a column vector, where we have each of the random variables going down from x1 down to xk, and our pi is our, so that's not pi, that should be mu. Our mu vector is all our mu1 up to mu k, and then finally the ijth entry of our sigma is the covariance of xi and xj. This still gives us our diagonal is the variance, because for example, the ith element of sigma, which would lie on the diagonal, would be the covariance of xi and xi, which we know is variance of I. Just going to go back now, we're looking at lots of variables, to this idea of the linear combinations we had before. So we're going to set up a complicated structure. We've got y1 up to ym, our collection of random variables, and we've also got an xi up to xm. We know the expected value of yi equals mu I, and expected value of xi is xi I. And we're going to say u1 is going to be a linear combination of the yi's, and u2 is a linear combination of the xi's. Okay, so this is probably as general as you can get. Well, you can show that the expected value of u1 is just going to be the sum of, from I goes from 1 to n, ai mu I. So basically we've got the idea of the fact that if you've got a linear combination of random variables, the mean of that is the linear combination of the means. Our variance of mu I, well, we've got this complicated structure. First of all, it's going to be the summation. You take all the coefficients, you square them, times it by the variance of ui. That's very similar. And then we have all those covariance terms. So basically we're going to go over all i's and j, as I goes from 1 to n and j goes from 1 to n. So we're looking at all combinations of the yi's. And we're going to have ai, aj, the covariance of yi, yj. We don't have to do the cases where I equals j, because that was already in the variance terms. And finally, with the covariance of u1, u2, we can just go over all the i's, all the j's, ai, bj, covariance of yi, xj. So these are just the general form of what we've seen before when we looked at linear combinations. Using that, we've got two theorems that are very useful in statistics. First of all, we've got the weak law of large numbers. So let's set it up and then think about what it is. So we've got an infinite sequence of random variables, x1, x2, all the way up. We know they all have the same mean and they all have the same variance. And at any point, we're going to stop and look at the ones we have so far, and we're going to count the sample mean. We're going to estimate the sample mean. And we're interested in saying, well, as we get more and more observations, and the sample mean has more and more observations in it, what's its property? And basically, we can show that the distance between your sample mean and mu, which is the true mean, the probability that that is greater than any arbitrary epsilon basically will go to 0. So what does this mean? Basically, it's saying that as your sample size gets bigger and bigger and bigger, your sample mean gets closer and closer to the true population mean, which is really good. It means that if we take a bigger sample, we get an answer that's closer to the truth. The next one is the central limit theorem. So again, we've got a sequence of random variables. They all have the same mean and they have a variance, and we're going to assume that variance is finite. And we're going to define this new random variable un, which is you take the sample mean, you take off the true population mean, and you divide it by the population standard deviation sigma over root n. Obviously, just to remind you, this is a sample mean, we add them all up and divide by how many. And then basically the key fact is the distribution of un converges to a standard normal distribution. Now you may have heard that basically x bar, as long as your sample size is sufficiently large, is approximately normal. And that's what we're saying. We're saying that as it gets, your n gets larger and larger, your un converges to a standard normal. That is for all u. The limit as n goes towards infinity, the probability un is less than or equal to n is, as you can see, is the integrand from minus infinity to u of a standard normal. It's really useful. Whatever your distribution, as long as it's sufficiently nice, and by sufficiently nice in this, we mean that it has a finite variance. As your sample size gets larger and larger, your sample mean has a normal distribution, so you can very quickly do calculations. Okay, so there was a quick introduction to the bivariate normal and the general multivariate normal, and we did some more linear combinations as well. And next time we're going to start looking at conditional expectation. See ya.